As we discussed in the previous introduction to water, there are some fundamental characteristics in the water molecule that will have tremendous implications to soils and soil behavior and the processes that take place within the subsurface. We are going to review some of those again today, and then we are going to advance to cover the contents presented here. Water is the only element that can be found in the three phases on Earth. Ice, for example, in Antarctica and the top of the mountains, vapor in the clouds, and liquid covering most of the Earth. It is so important to realize that water is a dipole, in fact, that it has a tetrahedral structure and that it is vibrating. Let's review those again. Please go back to see the previous introductory video for additional details. This is the polar molecule of water. And because of the preferential alignment of the hydrogens with respect to the oxygen atom, then it has this unique angle, and that gives water a very unique ability to orient in an electric field. The water molecule is about 2.7 angstroms in diameter, and if you think of the molar mass, there are two hydrogens with molar mass 1 and one oxygen with molar mass 16. Therefore, a mole, an Avogadro's number of water molecules, has a mass of 18 grams. Conversely, if you have a liter of water, and a liter of water is approximately 1 kilogram because of the mass density of water, then a liter of water, which is 1 kilogram, will pretty much involve 55 moles of water, 55 times Avogadro's number of water molecules. Because water is a dipole, in the presence of an electric field, molecules will orient in response to Coulomb's attraction force, where opposites attract and similar charges repel. Therefore, if I create an electrostatic field, and this electrostatic field has negative charges on the left and positive charges on the right, the water molecule will align because it will experience a torque. Now, that happens in a microwave oven 2,400 million times. In other words, 2.4 gigahertz, 2.4 billion times per second. And whenever that happens, there are collisions and something else, the hydrogen bonds will break. And so what is the origin of these hydrogen bonds? When we look at the water molecule into more detail, there are 8 electrons, and that means that there are 4 electron pairs. And that is to neutralize the nucleus, which has 8 protons, and there are also 8 neutrons, therefore the molar mass of water. So the hydrogens get aligned in that position because of the orientation of these electron pairs. But as you can see, on the other end, there are a couple of lone electron pairs, and these are going to give rise to this, which from a point of view of connectivity to other water molecules, looks like a tetrahedral structure. And that means that other hydrogens from the other water molecules will be attracted to those points, giving rise to hydrogen bonds. Those hydrogen bonds also get broken in a microwave oven and are part of the energy that gets absorbed, leading to a higher temperature. All these processes are happening very fast, much faster than a millisecond. But because of these hydrogen bonds, the water molecules do not pack in a dense packing, because as soon as they create a connectivity and other connectivities, they create a fairly open structure. And now we wonder, what is the porosity of water? I know it is a weird concept, but there are lots of pores in water that they are filled with nothing. There is nothingness, is a free space. And so we know that the molecule of water, because of this size, is about 11 angstroms cubed. We know that the molar mass of water is 18 grams, therefore it will occupy, totally, it will occupy 18 cubic centimeters. Here is the total volume. And the volume occupied by all the molecules in a mole will be Avogadro's number times the volume of a molecule, which is 6.6 cubic centimeters. Therefore, only that quantity is occupied by the actual volume that each molecule fills in, and the rest is free space. Therefore, the porosity of water is the volume of voids, which is the total volume minus the volume occupied by the water molecules, divided the total volume, 63%. Very high, but that gives unique opportunities, because in those pores, we can hide other molecules. For example, we can hide methane and oxygen and CO2. CO2 is a tricky one because it also dissociates, but then when we open a Coca-Cola bottle, all those CO2 molecules combine and they will nucleate and grow to form bubbles that eventually come out of club soda. But remember, we can also hide oxygen. This is not the oxygen that forms the water molecule, H2O. This is the free oxygen, which is oxygen 2. Gas molecules tend to be in pairs, as we will review in another video. And so these oxygen 2 molecules that are within the voids of water is what fish are able to breathe upon. In fact, we could run a test. We could de-air the water by some of the de-airing techniques that we use in our community, either applying vacuum and shaking it or boiling it, because gas doesn't like to be trapped in water when it is vibrating a lot. And then if we put a fish back into the water, then it wouldn't be able to breathe and it would die. So indeed, we have all this air and oxygen trapped and nitrogen trapped in water. Now, this is molecular dynamic simulations, and you see pretty much the way the structure of water looks. These hydrogen bonds are forming and dissociating, and there is a very large porosity. The only thing that is tricky in this simulation is that you can actually see it in real time. However, it is happening at very much higher speeds. Remember the frequency of the microwave oven? That's the frequency that the water molecule likes. So it is happening really in the gigahertz, while we see it here at relatively low frequency to be able to visualize it. But this is water molecules continuously vibrating and connecting and reconnecting, leaving high porosity in between. So now we have the foundations to understand how is water such an effective solvent, a universal solvent. So imagine the following situation. This is sodium chloride. This is table salt. The little ones are the cations, the sodium. The large ones are the chlorines. And in fact, you have to think that these are, they repeat itself in a mirror image in the back, and they form a simple cubic crystal. So when you look at table salt under a microscope, or even with a phone and a magnifying lens, you can see that they're all lovely little cubes. Now, this is a solid and this is water. Now, when I combine them, look what happens. The water molecules begin to go, the tail, which is more negative, it will go to the more positive cations, the sodium. See how they get organized. And the ears of the other water molecules will go, which are the positive end, will go to the negative ion, the anion, the chlorine, and eventually begin wedging in, and breaking these ionic bonds. And so the ions separate from each other, the crystal dissolves, and now we have hydrated anions and hydrated cations and other free water molecules. What you have just observed is the dissolution of salt to form salt water. Of course, if you put salt water on a table, let's say a droplet, and you come back the following day, the water will have evaporated and the ions will find each other again and the salt will precipitate. This is a molecular dynamic simulation. If you could see it behind, this comes from UCL. Apologies, the link has been erased by the presence of my video, but you saw it, and probably we will have to repeat it. You saw how that happens. Let's play it again. And so these are water molecules. All these are water molecules, but for clarity, you only see the ones that are approaching the ion. And now they are wedging in, and they are going to break that ion, and they take it away. They are dissolving the salt. So this is salt dissolution at its most elemental level, indeed, at the atomic level. So now you may wonder, can I keep adding salt forever? Well, not really, because you need enough water molecules to hydrate the ions. So let's say that each ion requires 3 or 4 water molecules. So a mole of salt, of table salt, will have Avogadro's number of sodium, Avogadro's number of chlorine, and you need 3 or 4 water molecules just to hydrate them, in addition to other free water molecules. So it gets to a point that you exhaust the number of water molecules. And this happens pretty much when you have about 6 molars in the case of sodium chloride. If you check the numbers, you will see that there are about 4.5 water molecules per ion. There is not much free water left, and therefore it cannot hydrate more salt. If you put more salt, this is a brine, and the salt will fall off to the bottom and will not be dissolved. Now, there are some salts that allow a very high concentration, like lithium chloride allows 20 moles per liter. And you say, how could that be? Well, because some salts get fully hydrated and the ions just separated from each other. Others may share the water molecule that hydrates one or the other, and others, they are hydrated on the periphery, but they still remain connected. So the pairs split from the solid salt, but the pair, each individual pair still remains in contact. And so in this case, you need lots of water. Therefore, the salt concentration at saturation will be lower than in this case. But in all cases, for all salts, you will reach a maximum amount of salt that you can dissolve. The same happens with sugar. When you put sugar in coffee, it gets to a point that you don't dissolve anymore, and you have solid sugar grains at the bottom of the coffee. Now, I mentioned before that we can get gas out of water by increasing the temperature. And the reason is because gas molecules vibrate so much that if you increase the temperature, they will find a way to escape. So while the solubility of salt increases with temperature because the thermal activity of water punches the salt more effectively, the solubility of gases decreases with temperature because there is so much mobility that the gas escapes. And this is what I'm showing in this data, that the solubility of gases, methane, oxygen, nitrogen, hydrogen, decrease with temperature. And that's the reason why we can be more or less effective at degassing water by boiling it. And while we're here now, we can recognize that there are different ways to purify water. One is to distill it, and that is you increase the temperature in certain phases that are, for example, if there was alcohol, it would evaporate at 50, 60 degrees. And then you let that component evaporate, and then you keep the water. And then when water evaporates, then you condense it, and you make that cut at about 100 degrees Celsius at 1 atmosphere, and you have distilled water. You can deionize water by selective adsorption or by reverse osmosis. And you can use activated carbon filtering, which is selective adsorption, and that's one of the ways we clean water in our homes. We will review these possibilities and why do we use the different ones in another video. Now, I also indicated in the preliminary introduction to water that there is a probability that water will self-ionize. In other words, it will split to form ions because the water molecule is electrically neutral, but if it splits, there will be a positive component and a negative component. How does that happen? Well, imagine that you have two water molecules. The blue one, the one with blue periphery, is one water molecule. The one with the black periphery is another water molecule. And these are all vibrating. And at some point, it is probable that this hydrogen that was leading to this hydrogen bond actually remains stuck to this water molecule, forming what is called a hydronium. The other one is hydroxide, OH. This is positive, this is negative, and this is positive. So now we have two ions. That doesn't happen very often. It happens at the rate of 10.7 moles, so 10.7 Avogadro's number per liter. Now remember that in a liter we have approximately 55 moles of water, and so if I divide numerator and denominator, then we get about 2 hydroxides for every billion molecules of water. Very, very small. But still, in an electric field, they can migrate. The hydroxide, which is negative, is the anion, will go to the anode, and the cation, the hydronium, will go to the cathode in a pair of electrodes. But there is very small movement of these ions because they are very small, so the electrical conductivity of water is minute. It is measurable, but it's minute to the point that we say it's a dielectric. Pure water does not conduct electricity, but in reality it does a little bit. The other important consequence of this is now, because OHs and excess hydrogens are so important for all geology and for our lives, in fact, we are going to define a unique quantity. We don't call it concentration. We're going to call it pH. And pH is defined as the minus logarithm in terms of the molar concentration per liters of hydronium or hydroxides. And so if you do that, the minus log of 10 to the minus 7, then you get that is 7. So under normal conditions, the pH of water is 7, means that 2 molecules per billion molecules of water have formed ions, have self-ionized. That is the equilibrium condition. Now, we can change the pH by adding more hydrogens. How do we do that? Well, we put an acid, hydrochloric acid, or we can add more hydroxides by adding sodium hydroxide. And so we are feeding hydroxides, we go on this side, or we are feeding hydrogens, and we go towards the formation of hydroniums. And so we lower the pH or we increase the pH. The system is electrically neutral. This was electrically neutral, this is electrically neutral, this is electrically neutral. Still, we have these ions that can be quite aggressive for many minerals. Let's see, for example, what happens when we put CO2. I said that the story was more complex. We can hide CO2 in water to form club soda, but when we put CO2 in water, it forms carbonic acid. And so when it dissociates, the pH goes down because we have the formation of hydronium. So there is more hydronium, there is more hydrogen, and we have this anionic component. Now let's inject a bubble of CO2 into water with a pH color indicator, a universal color indicator. And this is time-lapse photography. It doesn't happen so fast. But you see the initial gas bubble is decreasing in size because CO2 is dissolving in water, but also there is a halo of yellowish color, meaning low pH, that is propagating. So dissolution is taking place as the carbonic acid diffuses into the water. And in fact, at some point, the rate of dissolution here is limited by how fast carbonic acid can diffuse out. So notice that during CO2 geological storage, we're going to have dissolution and acidification and diffusion taking place. We are looking here with a microscope, we are looking at something that is happening everywhere, wherever we're going to store CO2, or in the subsurface atmosphere interaction where CO2 is continuously being absorbed as part of the carbon cycle. I said earlier that the importance of pH is that it causes dissolution, and it will cause dissolution either at very high pH of this magnesium hydroxide, it gets the solubility decreases, or at very low pH, like for example, calcium carbonate at pH as still fairly high, as the pH drops before 10, 9, it will begin dissolving. The solubility increases dramatically. So we can experience dissolution at high pHs or at low pHs because each mineral likes its own equilibrium pH with the surrounding water. This also gives us one more thought. Soils are not inert. They are continually changing. They do it in longer time scales than our life or typical engineering scales. But this is not true anymore for some of our engineering tasks. For example, geological storage of CO2, where we have to design for thousands, 10,000s of years, at least as we go through the whole energy transition and we re-equilibrate the CO2 concentration into the atmosphere. Now, because water is continuously vibrating, if you think of the water-air interface, don't think of something static anymore. You have to be thinking that some water molecules are jumping out and some water molecules in vapor are jumping back in. And there is a continuous bombardment of this water in the vapor phase that are actually creating what is called the vapor pressure. As I mentioned earlier, if you put table salt in water and then you make a droplet of salt water, you put it on the substrate and you let it dry, the water will escape, the ions remain, and they recrystallize, in this case, because it is table salt and likes simple cubic packing, it recrystallizes, forming these lovely cubic crystals. Once again, this is time-lapse photography. The reality maybe it took 10 hours, 20 hours. Now, as I mentioned earlier, if you put too much salt, you may have brine that cannot dissolve salt anymore. And this is the situation that we see in many places where we have water bodies, for example, the Dead Sea. It's a water body surrounded by salt precipitation and involved in salt precipitation. And there is water in the pond, in the lake, in the Dead Sea, but it cannot dissolve the salt anymore. If it rains, it will dissolve some of the salt. If it doesn't rain, which is the case in most places where we have this type of formations, water evaporates and continuously precipitates additional salt. Now, the next issue I would like to say is that water not only hydrates salt, but if you think of a clay layer, and a clay layer tends to be charged, and there will be counter ions stuck to the clay layer to neutralize the clay layer. So if the clay layer is negatively charged, there will be calcium, sodium, potassium, magnesium, the most common cations, stuck on the clay surface, neutralizing it because of Coulomb's force, QQ over R squared. The Coulombian attraction is so strong that nature wants to be electrically neutral. Now, if you begin throwing water molecules at a dry clay, it will begin to absorb the water molecules, and the water molecules will begin bombarding those counter ions. They will hydrate them, take them away from the clay, but they're still attracted to the clay. And this is the formation of double layers, a topic that demands its own video review. But if you control the amount of water that you throw by controlling the suction, then, which is the variable on the horizontal axis here, you begin allowing for 1 monolayer of water, 2 monolayers of water, 3 monolayers of water to absorb while it is hydrating the cations, and this is the origin of swelling. So let's see what happens. That is the dry clay with the counter cations. In this case, we're assuming that it's negatively charged. We add water, and water goes in, wants to absorb onto the clay surface, putting the positive, the hydrogen next to the negative charges, the location of the negative charges, hydrates the cations, but the cations cannot go too far because the clay is still charged. This didn't neutralize the charge, and the hydrated cations are also charged, so there is attraction to the clay and repulsion by the thermal activity of water that keeps kicking them out. So we can see, if we take a snapshot of a molecular dynamic simulations, once again from UCL, then you see the hydrated cations around the clay, separated from the clay by water molecules in most cases. Some of them could remain stuck, particularly if they are small cations, forming what is called inner sphere complexes. But in general, what you see right there is the diffuse double layer around clays. We have mentioned the word diffusion already a couple of times, and we have to wonder what diffusion is. Diffusion is random walk. So if we take lots of blue balls, and they are vibrating, and they can migrate, and these are on the other side of the experiment. We have yellow balls, and they are doing the same thing, probably because you sit them on top of a vibrating table, and eventually they begin mixing, and in the end, they are totally mixed. So this is random walk, and Einstein came up with a very neat equation. This is the thermal activity, this is viscosity, and these are the charges, and now you can relate the diffusion coefficient at the very fundamental level to thermal activity, the size of the ion or hydrated ion that is moving and is migrating, and the viscosity that is migrating through. It's a tricky equation because we have equivalent continuum parameters like viscosity together with the atomic scale parameter, which is the size of the charge that is moving. Now, in soils, this random walk is affected by the presence of grains. So it has to go around grains. So the effective diffusion coefficient in soils gets diminished by the tortuosity of the path created by the porous medium, by the grains packing next to each other. So tortuosity comes into the picture, decreasing the macro diffusion coefficient in the liquid. But then there is something else that happens, that as the soil particles get smaller, the voids get smaller. And when the void gets smaller, the random walk now is affected by the presence of the wall. In fact, we go from what is called fixed diffusion at large pores to what is going to be called Knudsen diffusion in small pores. But without going into further details, the diffusivity, the effective diffusivity of different ions decreases as the pore size decreases. Clearly, if the pore size becomes the size of the ion, then the diffusivity has decreased by 4 orders of magnitude. In general, when the pore size is 100 times larger than the ion, then pore size does not affect diffusivity. We still have the tortuosity effect. So look, this is the squares are data for kaolin, the circles are data for bentonite at different levels of compaction. So same specific surface, but we are reducing the void ratio. And this is data for permeable membranes with very well-known pore size. So this is diffusion, is random walk. Now let's understand the other concept, which is osmotic pressure and osmosis. So this is a typical experiment. We have a semi-permeable membrane that it will allow water molecules to go through, but it will not allow hydrated ions to go through. So when we look at the membrane here, and there is higher concentration of salt concentration on the left, there are fewer free water molecules knocking at the door. On the right-hand side, we have very low ionic concentration. These are the hydrated ions. And so there are more free water molecules knocking at the door. So there will be more free water molecules going from the right to the left. In other words, ions are vibrating here, diffusing here, but they cannot go through the membrane. Only water does. And there will be more migration of water from the low concentration to the high concentration. Therefore, if I run this experiment, I start with these communicating tubes at the same elevation, and I run the experiment for a while, water will go into the high concentration region, and this column height will go up. And because this column height will go up at equilibrium, the difference between the two heights of the column will tell me the osmotic pressure. So the difference between the column heights is the pressure that is forcing, that the traveling water is forcing through this membrane. Conversely, if I apply a higher pressure on the left, it will force water molecules to the right. So that is when this balance is reached. Now that allows us to explain many things at the clay level, but before I go there, let me make the following observation, that seawater has this concentration, 35 grams per liter, while our blood has about 9 grams per liter. So if we drink seawater, and seawater goes into the GI tract, and this is a semi-permeable membrane, we're going to have high concentration inside the tube, low concentration in our body. So according to the skin on the left, water will go from our body into the GI tract. So in fact, we are not going to hydrate, we're going to dehydrate. Water is going to be pulled out from our body into the digestive system. And now you can have some conclusions as to why Gatorade and Powerade use the salt concentrations that they choose. This osmotic pressure also happens between two clay particles. So between two clay particles, we have high ionic concentration because of the counter-ion cloud. There are lots of ions that need to be there to compensate the charge of the clay. So this water here tends to have high ionic concentration. However, if the water in the pores has low ionic concentration, then water will be knocking at this virtual interface. There is no interface, but these ions cannot escape because of a Coulombian attraction. So this water molecules, there are more free water molecules on the large pores than in the pores between the clays, and they are creating an osmotic pressure that wants the clay to swell. And we can compute now that osmotic pressure from the Van Hoff equation, the same as we did in the case on the left. Now we can compute it, but there is no membrane. Remember, it's a virtual membrane just because of the fact that these ions cannot go far away because of Coulombian attraction. This osmotic pressure forces swelling when the pore fluid going through has low ionic concentration. The opposite could happen if the pore fluid that goes through has very high ionic concentration, like now salt water, seawater intrusion due to sea level rise. Now this water will have higher ionic concentration. The osmotic pressure will go in the opposite direction, and there will be contraction of the clay, chemoosmosis. And we see these effects throughout all the swelling clays around the country, around the world. Now I'm going to talk next about the temperature and thermal properties of water because they are so unique and it has huge implications to soils. So remember, we started with the fact that water is actually a tetrahedral structure. So when we begin lowering the thermal activity, we allow that thermal structure to really take over, and the molecules get increasingly more and more organized. And so by the time we go through 0 degrees Celsius, thermal activity really has decreased to let the structure prevail. Ice forms, and ice forms with characteristic crystallographic structure. This is the formation of ice. And in so doing, this structure now occupies more volume, and so there is volumetric expansion. Now, still in those holes, we can hide molecules. For example, we could hide a molecule of methane, and this is called methane hydrate. It's a methane molecule trapped in a cage formed by water molecules, which are organized because of that unique tetrahedral structure of water. This is considered one potential source of energy for the world, and many countries are exploring it, the US among others, but with more interest probably in China, India, Japan, Korea. So what are some of the most unique properties, thermal properties of water? Well, as water heats up, it expands the volume. It's volume dilation. Conversely, as the water cools off, it contracts and it gets denser and denser. But as we said earlier, when it forms ice, it expands. So this contraction is the maximum density is reached at about 4 degrees Celsius in pure water. With salt water, there is a little bit lower temperature, but it's about that temperature. And so the densest state of water, let's say that is 4 degrees Celsius. And now let's think of what happens in the ocean. As the ocean gets deeper and deeper, it doesn't feel the sun anymore. The water gets cooler and cooler, denser water goes to the bottom, and the bottom of the ocean is at 4 degrees Celsius. And at that point, if this is the seafloor, it will pick up the geothermal gradient between 30, 35 degrees, and the temperature increases. But in the water column, the temperature remains more or less, let's say 20 degrees in the upper 100, 200 meters, but then it gets cooler and cooler and denser, and because dense water goes to the bottom, then this is where the densest condition is. Upon freezing, water experiences 9% volume expansion, 9%. Therefore, ice floats on water. And the balance between that density and the density of water is that we only see the tip of the iceberg. It's not just a standard phrase, it's the actual, and we only see a small volume of an iceberg floating, and the rest is sunk in the water body. Now, during liquid to gas transformation, the expansion is huge. The expansion is actually 1,700 times, no percentages. The previous one was 9%. That means 0.09 volumetric expansion. This is 1,700 times. And this is phenomenal. This was the great discovery that led to the steam engine and the Industrial Revolution, but also to many geological features. So if there is a magmatic intrusion taking place and it hits the water level, that water will expand so much that it creates a massive explosion, like this is called the Wawa crater, because of phreatic eruption. This is probably like 2 kilometers in diameter, the diameter, 7 kilometers in diameter. So this is really a very large feature. Now, because of the hydrogen bond, all the thermal constants of water are pretty much unique. So the heat capacity, it takes lots of energy to change the temperature by 1 degree Kelvin of 1 gram of water. It takes huge amount of energy to convert ice to water or water to vapor, and the thermal conductivity is very high. Let's put this in perspective. Let's compare the energy of melting ice or forming ice in either direction of your reaction, of your transformation. Let's compute that energy to the energy to heat water. And so we made that ratio, the heat capacity and the latent heat. And it would, the same energy that is required to heat water from 0 degrees to 79 degrees is the energy that is required just to freeze the water. No more energy, no more temperature change. From 0 degrees liquid to 0 degree solid, we have invested the same amount of energy as to increase the temperature of water from 0 to 79 degrees. Huge. But it's even greater to vaporize water. If we do the same ratio, the energy that it takes to go from 100 degrees liquid to 100 degrees vapor, just that phase transformation, no additional temperature change, just to transform the phase from liquid to vapor and to break all those hydrogen bonds is huge. It would be the same as to increase the temperature of water from 0 to 537 degrees. Of course, we couldn't do that. It would vaporize before unless we do it in a pressure cooker. But the transformation of phases are always very energy intensive. And so in our geotechnical processes or in mining processes, etc., we always want to avoid doing a phase transformation. That's the reason why the dryer for drying clothes at home is so energy consuming, and the freezer is such an energy consuming. Those two are responsible probably for 90% of the energy that we consume in our home. Light has a very minute contribution. That is also important because water plays a critical role in moderating climate change. And we know it, for example, the extreme temperatures in the desert between day and night comparing to the temperatures in day and night in tropical regions. And that is because the moderating effect, all because of these properties. Now, the volumetric thermal expansion is really so notorious. And this is liquid just being warmed up, it expands. And we don't realize it, but actually we can observe it in our kitchen. In a jar, we can see that volume expansion. And imagine now that we increase the temperature of the ocean, which is 3.7 kilometers deep by 1 degree Celsius, it will experience a sea level rise of 0.8 meters. In fact, this is a very important component of sea level rise. It's not just the melting of the Arctic and Antarctic Sea, is the warming up of the ocean and the expansion of the water. Finally, on this theme, I would like to say that when we combine the tendency to expand with the stiffness of water, now I could take a container and close it, warm up the water, and because it wants to expand, with the stiffness with the confining pressure are opposing the expansion. So when we do that balance, that the volumetric expansion under control volume isochoric conditions we set it to equal to 0, so we don't let it expand. That means that the tendency for volumetric expansion due to thermal change must be equal to the tendency to volumetric contraction because of the water pressure that we are inducing, dividing the bulk stiffness. Therefore, now I can compute what would be the pressure that I would generate if I produce a thermal change delta T in water and you don't let it expand. Well, for 1 degree Celsius, that would be 450 kPa. And that's the reason why every device in the laboratory where we measure pressure is actually a great thermometer. We have to make sure that our experiments are conducted at very stable temperature conditions, and our laboratories often vary in more than 2 or 3 degrees. And what can happen if you don't do that? Well, this is the case. The expansion can be so pronounced that this is kaolin that was mixed with water, let's say something close to the liquid limit. You put in the microwave oven, it completely hydraulically fractures inside because of that water expansion. And you may think that that is extreme, that happens only in the microwave oven, but let me show you an example. This is a very large structure. You see a hydraulic fracture, you see the actual propagation of the hydraulic fracture. And the reason is because lava went over this formation. All this was buried. Lava went over this formation. This formation was wet, humid, and the expansion of water produced the hydraulic fracture. And all this formation is massively hydraulically fractured. This was part 2 in our review of water, and I hope you realize the important implications it has on our understanding of soils, our understanding of geoprocesses, implications to laboratory testing, the implications of saltwater intrusion and swelling clays and contractive effects. There are a few more wonderful things to discuss about water, and that will be in subsequent videos. Thank you.